some reason you think I can skip some slides, there's no problem. Just tell me and I go to other stuff. But I assume it will be okay. But you should know that just in case, if you get bored, I can show you more things. And so currently I'm in Munich. So I'm affiliated to Padova and the Max Planck in Munich. But I will start a new group in Hanover from 2023 with this, what is called this Emmy Noether Fellowship. All right, so let me start the talk. Let's go. So let's see. So let me give you a little bit of context of what is my interest and what I have in mind. And for that, I draw this picture where I show you, say I divided, this is the universe, our universe, and I divide it into what we can see, what I call the explored universe, and what we say haven't explored yet. This is the unexplored universe. Yeah. And then this explored universe is what we have observed with electromagnetic waves. Okay, so if we are sitting on Earth and we look with our telescopes, we find stars, galaxies, clusters of galaxies. And then as you look farther, you are also looking into the past. And the first signal, so the most distant signal that we can observe is this cosmic microwave background here. And from the cosmic microwave background, we have learned a lot about the early universe. For example, we learned that the early universe was made of a plasma of relativistic particles, and quite importantly, that this plasma was filled with primordial energy density fluctuations. And these energy density fluctuations actually tells us that they had to be generated much, much before. So we know there's something beyond what we have observed already, and it is what I call, or usually it's referred as the primordial universe. And about this unexplored universe, we will have the chance, hopefully, to explore it a little bit more using gravitational waves. And here I just draw two crude analogies. So for example, if you want to explore the bottom of the sea, you should not use optical light, but for example, you can use something else like sound waves. Or if you want to study the core of the sun, you can use neutrinos. So they come directly from these regions. So gravitational waves will play a similar role. So they will carry information from this unexplored universe with electromagnetic waves. And for example, we could learn something more about inflation, which is the mechanism that generated all known fluctuations in the universe, especially these primordial fluctuations. But we can also learn about anything that happened since inflation and afterwards, maybe some new interactions, new particles, and many other things we could happen here. Right? So gravitational waves have the potential to probe the unexplored universe. And here, so I now, this picture is from today to the past. Now let me zoom in this primordial universe, inflation and cosmic microwave background. And this is the typical picture of an expanding universe. So you have time going to the right, and then some representative, say, scale factor or anything, it's expanding. Right? So the universe is growing, it's expanding. And you can see two colors here. One is the green, which means something we have explored with electromagnetic waves. For example, here is the last scattering surface when the CMB was emitted. And we know at least until 1 second after the Big Bang, around energy, MEV, neutrino decoupling, the universe was dominated by radiation. So this part, we understand it quite well. And then we can also know about what happened in the primordial universe. We have strong evidence of inflation because we see these anisotropies of the CMB. So with what we have observed with electromagnetic wave, we have strong evidence that there was at least some period of inflation. But we have only probed a small part of inflation. We haven't probed what happens later towards the end and how the universe was reheated, so how we achieve the standard cosmology. Okay, so how standard model particles were created and so on. And especially in this epoch is where gravitational waves can tell us something. And here I put some example. So let me remind you what inflation does. Inflation takes quantum fluctuations, small quantum fluctuations inside the cosmic horizon. It stretches them out of the horizon. So you have some fluctuations which are now frozen. And then inflation ends, okay? And the cosmic horizon grows, which means that the fluctuations will at some point enter in causal contact, will enter the horizon again. And they start to evolve, they start to do their stuff. One possibility is that these fluctuations are so large, at least some of them, that they collapse and they form primordial black holes. Okay? These primordial black holes can survive until today, and you can see the measures. But these fluctuations, they also generate some waves in the fluid, and these waves sort of generate gravitational waves, and this is what we would see. Okay? So this is the scenario that I have in mind. There are other sources, but I will focus only on this. So why should we care about this possibility and about gravitational waves from primordial fluctuations? So I have this slide, especially when I talk to some astrophysics group and so on. I guess your group really is interested in maybe primordial cosmology. But in case someone is not so interested, let me tell you why should you care about this. First of all, this primordial or gravitational waves, they carry new and fresh information. This is something we have not explored yet, so we may have some expectations, but we don't know exactly what could it be. And to show you that, I draw this sort of energy scale frequency, this drawing here. So in the left, you have the frequency of the gravitational waves. So kilohertz, hertz, you have LIGO, Virgo. Then maybe, hopefully, the LIGO will cover from hertz to millihertz. Then you have LISA and pulsar timing arrays. And now if you take this frequency, so the frequency of the gravitational waves, and you ask what was the energy scale of the universe when it was of the same length scale, okay, then you obtain these results here. So for kilohertz, you get up to 10 to the 11 GeV. For nanohertz, is around 0.1 GeV, so 100 MeV. So you're covering a huge range of energy scales in the primordial universe. And of course, many things could have happened here: phase transitions, cosmic strings, axions, anything that you like. And having a lot of possible cosmic gravitational wave spectra is also good for astrophysics. So even though I would not be happy if this happens, so that you find no cosmic signal, at least if you are sure that it's not a cosmic signal, then you can focus on the astrophysics. You can say, I'm very sure that it's a clean astrophysical signal. Then you can do something interesting too. And so let me say there's an interesting window here in the pulsar timing array, where there are already some hints of a gravitational background, although we need to wait for confirmation, and actually falls in the QCT phase transition, which curiously enhances the production of primordial black holes. And the measures could be seen in the LIGO Virgo window. So in the future, we may find something like this. Here I show the spectral density of gravitational waves versus the frequency. And again, I emphasize which energy scale corresponds to each frequency. So nanohertz and 100 hertz, you have 10 to the 10 GeV, 100 MeV. And then I show some typical, this is a very prototypical spectrum. As I say here, this will depend on the expansion of the history, but if you extrapolate the standard cosmological model, so everything is radiation dominated and since inflation, you could find something like this. So a flat spectrum could be cosmic strings, a bumpy one, some first order phase transition, and the induced gravitational waves are typically a bit more spiky. But okay, so today, I will focus only on this, what is called the induced gravitational waves. So let's talk about these gravitational waves. I organized my talk into 3 parts, but I think I will only talk about 2 of them. And if I have time, I will go to the 3rd one. First, I will explain to you how these gravitational waves are produced and what information they carry in 3 simple messages. Okay, so please pay attention here. There are 3 simple messages that I hope it will help understand these induced gravitational waves. Then I will talk about the primordial black hole dominated universe, which is a very loud universe in the gravitational wave signals. I find this quite curious and interesting, so I will jump the second part, and I will go to the primordial black hole dominated universe. And if in the end you still have energy and you want to know about how the expansion history changes the spectrum, I can also talk briefly about this. So let's start with these 3 messages. Okay. So yes, I have this history slide. So if you're just curious about who was the first one to point out this effect, it was a Japanese, Kenji Tomita, in the 71, so a long time ago. And then it was rediscovered in the 90s by Matarese, but it was not really until 2006, until 2008 that the real potential of this effect was realized. And then it was sort of quiet until we had the first detection of gravitational waves. I might have a review paper. If you want to check more about this, you can look at it. So what are these 3 messages? The first one is that any space-time fluctuation induces gravitational waves. Okay? So this means any fluctuation you have in your universe, okay, will have some gravitational wave counterpart. For example, you have density fluctuations that are generated by inflation, and these density fluctuations, they evolve, they oscillate, and somehow they shake the metric, they shake the space-time, and these vibrations, they propagate as induced gravitational waves. You will have some spectral density, with frequency, some profile. Okay. So you give some initial conditions, these gravitational waves are generated, and in the end, you see the spectra. Now, the second message is that induced gravitational waves are messengers of the unexplored universe. And let me explain what I mean by this with an analogy. So if you think of the primordial universe as a bell, so the space-time as a bell, the density fluctuations could be a hammer that are constantly hitting this bell. And induced gravitational waves is the sound that you receive. So you can trivially see that if density fluctuations are very hard, very strong, then you will have a loud gravitational wave signal. But you can also learn something more if you hear the pitch. Okay? So you could maybe tell something about the composition of the bell, or what was the medium in which this sound propagated. So all of these will be encoded in the spectral density of the gravitational waves. Okay? So induced gravitational waves are sensitive to the content of the universe in which they were generated and they were propagated. And here I have 2 examples. So this is roughly the spectral density when the universe was made of relativistic particles. This is the prototypical case. But if instead it was made of non-relativistic particles, you would get a very different spectrum. Okay? So just a single peak and some tail. So definitely the spectral density depends a lot on what was the content of the universe. And this is an important piece of these induced gravitational waves. And the last message is that primordial black holes are related to these induced gravitational waves. So the first message was that density fluctuations generate induced gravitational waves, but the same density fluctuations, some of them, will be large enough that they collapse and form primordial black holes. So the origin of these 2 observables, the gravitational waves and primordial black holes, is the same. There's some density fluctuations with a typical wavelength or typical scale. And therefore, they will share some link. For example, the mass of the primordial black holes, which will be related to the size of the horizon where they collapse at, or so the typical density fluctuations, will be related to the typical frequency of these gravitational waves. And for example, if you assume a radiation-dominated universe, you have this relation. So the peak frequency of the gravitational waves is around hertz for a primordial black hole of 10 to the 16 grams. So this falls into the Lisa band if you have maybe asteroid mass primordial black holes. But again, this relation will depend on the content of the universe. So now we can do some order of magnitude estimates. Actually, not too bad one, so it's quite precise. Oops, sorry. How do I go back here? So for that, I need to present to you the equations of these gravitational waves in cosmology, so in cosmological perturbation theory. So at first order in perturbation theory, just as you would expect, you have free wave propagating in the universe. But at second order, so since general relativity is nonlinear, you will have some source term, which will be quadratic in the perturbation. So here I wrote the curve of the perturbation, but could be density fluctuations or velocity fluctuations. Any scalar contribution will source at second order these induced gravitational waves. And just by knowing that, so the tensor mode Hij has to be proportional to the square of the scalar fluctuations, just put this naively here. So this is the spectral density. It is the power spectrum of induced tensor modes. So then you put this has to be proportional to the square of this curvature perturbation, and then you take into account just the redshift, and you can do that by putting in the density ratio of radiation today. So if you put some numbers from Planck, we know this is 4 times 10 to the minus 5, the fraction. So in the end, you get 10 to the minus 6 times the power spectrum square. And this is quite good for a radiation-dominated universe. So in this way, you can estimate what is the peak amplitude of these induced gravitational waves. Now, if you use the CMB normalization, this power spectrum of curvature fluctuations has an amplitude of 10 to the minus 9. So the square is 10 to the minus 18, minus 6, 10 to the minus 24. This is too small to see it. But actually, the frequency of this, the frequency range of the gravitational wave detectors correspond to scales much, much smaller than the CMB. And we don't know actually the amplitude of the primordial spectrum on these scales. So it could be larger. So let me show you when we will be able to see that. Here I show again the spectral density, now in terms of log of the spectral density and log frequency, and some sensitivity curves for several detectors. Pulsar timing, LISA, the SIGO, LIGO, and Einstein telescope. These are the so-called power law integrated sensitivity curves. This just is to give a rough idea how sensitive the detector will be to stochastic backgrounds after they have waited for a long time. And so here I plot the dashed line. I plot this order of magnitude estimate. So if you have the primordial spectrum about 10 to minus 4, you can see it maybe in the pulsar timing array or in the future by the SIGO. But if you increase the amplitude at 10 to minus 2, then it should appear everywhere. Plus, you will have a detectable primordial black hole counterpart. So in this case, you will have 2 observables to test this model: gravitational waves and primordial black holes. Now, but as I said, there are many ingredients going on here. So let me explain to you how the spectral density will depend on the different pieces. Okay. First of all, you will need to give, so if you want to compute these induced gravitational waves, you have to give some initial conditions. Okay. Initial conditions, in this case, are given by inflation. And it will depend on the shape of this primordial spectrum of fluctuations. Okay. And this, of course, will depend on the physics that generated this enhancement of fluctuations. And now you have various possibilities. So was it generated during single field or multi-field? This might change the spectrum. Is the spectrum sharp or broad? Or are the initial conditions adiabatic, or are they isocurvature? So you have several questions here that will depend on the model of inflation. So once you have given the initial conditions, then you have to evolve to solve the gravitational waves when they are generated. So these waves are generated after inflation. so during this primordial universe. So you have to know what was the universe made of. Okay, so you need to know what was the question of state of this primordial universe. Was it dominated by black holes? Anything that could happen here will affect the generation. And then, depending on the initial conditions and depending on the primordial universe, you will see some gravitational wave background. Now, there are questions like how you tell them apart from astrophysical ones, or what happens if they are buried inside the astrophysical signal. There is some interesting issue with the theoretical definition of energy density of gravitational waves. I will not be able to talk about this, but if you are curious, I talk about this in the review. Okay, so these are the three pieces for computing induced gravitational waves. Now, let me see if this is clear. Do you have any questions on this introduction? No? Then let me go to the primordial black hole part. Yes, okay. So just to remind you what is happening. So you have, this is the expanding universe, you have inflation, that some fluctuations are generated, so large scale fluctuations generated in the beginning of inflation, and this affects the CMB. But small scale fluctuations are generated towards the end of inflation, and they generate, say, these induced gravitational waves after inflation, during, say, the reheating epoch. So let me skip this part, and let me go directly to the primordial black hole dominated universe. So what is happening here? Let me try to show you with this plot what I have in mind. So I will assume that after inflation, we get to some radiation dominated universe, and that for some reason, some primordial black holes are formed, okay? And they will be formed with some initial fraction called beta. And here I show this is the energy density ratio of the two fluids. I will assume it's only radiation and primordial black holes with number of EFOLs. So you see in red, you have radiation, and in blue, you have the primordial black holes. These primordial black holes behave like a pressureless fluid. So the energy density does not decay as fast as the radiation. And at some point, they will dominate the universe. So if the initial fraction is not too small, they will eventually dominate the universe. So depending on the initial fraction, they will dominate earlier or later. But I will assume that these primordial black holes are very small, so are actually so small that they evaporated much before Big Bang nucleosynthesis. And so this epoch of primordial black hole domination, this era of primordial black hole domination, they will end eventually because of Hawking evaporation. And so here, this is an important point. I will assume that these black holes have a monochromatic mass, okay, so a single mass. This means that all black holes will evaporate at the same time here. So independently of the initial fraction, there will be a moment where all black holes just disappear and radiation dominates the universe.
Why would you assume that they all have the same mass?
Yes, why? Because if not, it gets very complicated.
Oh, fair enough.
We can talk about later what happens if you want. Yeah. So this is a crucial assumption. So I can tell you later what happens. Right. What did I want to say? Yes, and then we will come back to a radiation dominated universe. Say the standard one. The evaporation. Yeah. Sorry.
Sorry, I coughed.
That wasn't a question. Someone just.
That wasn't a question. I just coughed. Okay. Yeah. So this is evaporation because they are monochromatic. The mass function is monochromatic. Will happen very fast. So here I show you. This is the last EFOL, and this evaporation happens in the moment when dark matter, this primordial black hole, they disappear and radiation dominates, happens in less than a quarter of EFOL. So this happens very fast. So it turns out that if you compute these induced gravitational waves in this scenario, it gives a very loud signal. But before I can tell you how to compute these induced gravitational waves, I have to remind you about something. So let me tell you about these initial conditions of the initial condition of the perturbation. So there are two kinds of initial conditions you can give. So one is the so-called adiabatic initial conditions, and the other one, the isocurvature initial conditions. To understand this, you can look at the 0-0 component of Einstein equations in this so-called Newtonian gauge, and you will find this on superhorizon scales. This means the curvature fluctuations are proportional to the total density fluctuations. Now, okay, so this only cares about the total density fluctuations, but you can also have some relative fluctuations. If you have more than one fluid, you can have relative density fluctuations. And this is parameterized by the isocurvature S. If you want adiabatic initial conditions, you are asking that there is no isocurvature and you are only starting with some initial curvature fluctuations. But you can also start with vanishing curvature fluctuations and having only isocurvature. Okay, for example, colder matter isocurvature means this. So initially, no curvature fluctuations, just some relative density. So the total density fluctuation, they compensate each other and it's 0. This could be due to extra fields during inflation, but this is actually what happens when primordial black holes are created. Okay. So let me explain you how primordial black holes, when they form, they actually create isocurvature fluctuations. So now imagine you have, so you end inflation and you start with a radiation-dominated homogeneous universe. So this is what I draw here. You have energy density in the y-axis and say space in the x-axis. Radiation is homogeneous, so this is constant. And I don't care about adiabatic fluctuations because adiabatic and isocurvature, they evolve independently. So let's start with this homogeneous universe. Then I assume that something happens. And for example, you have a large adiabatic fluctuation that starts to collapse, and you form a black hole. Okay. So the mechanism, how you form it, I don't care too much. Just that we started with a homogeneous radiation-dominated universe, something happens and you have a black hole. Okay. Now what happened is that, it wasn't a question, it was a cough again? I think so.
Oh, sorry, it's background noise.
So what happened is that, as you can see, you started with a homogeneous universe, but some of the radiation went into black hole. So if you look into some coarse-grained picture, in reality, this is a hole, but just to show you for later purposes. So you take a coarse-grained picture and you will see that the energy density of radiation decreases, and now you have, say, some energy density associated to the black hole that now compensates the missing one. So this is actually the condition for isocurvature fluctuations. So when a primordial black hole forms, you start to have something like isocurvature fluctuations. Now this is very simplified, you just have one black hole, but you will actually form these primordial black holes randomly in space. Okay? And all this collection of primordial black holes will in the end lead to these isocurvature fluctuations. You may have something like this. So you have a collection of primordial black holes with some mean energy density, and then this sort of isocurvature fluctuations following the distribution of these primordial black holes. Is this clear? I hope so. And then, so these are the initial conditions after black holes form. So after PBH formation, you start to have isocurvature because of the inhomogeneous distribution of these PBHs. And now you evolve the system. Since these primordial black holes, they behave like cold dark matter, they behave like pressureless fluid, the ratio of energy densities will increase, and you will have something like this. Whoops. Now the relative weight is smaller, so primordial black holes start to dominate a little bit more, and all these initial isocurvature fluctuations start to source adiabatic fluctuations. The amplitude of fluctuations is proportional to the energy density ratio. So in the beginning, it will be small. So you will generate gravitational waves, but with a suppressed amplitude. So I'm interested in the case when these primordial black holes dominate the universe. And when this happens, all this initial iso-curvature has been converted to adiabatic fluctuation. So now you will have huge adiabatic fluctuations, huge curvature fluctuations when primordial black holes dominate. So you can understand why this happens. And this is essentially because, so the fluid that dominates is the one that gives the curvature fluctuations. So if you started with some small density fluctuations in the cold dark matter and eventually cold dark matter dominates, you will carry these fluctuations to the curvature part. And now this will induce large gravitational waves. So what happens now, including the gravitational waves, is this. We start with a small fraction of primordial black holes. You generate some induced gravitational waves, but they are not so interesting. Then primordial black holes dominate, and you generate some rather large signal during this PBH domination. And then black holes evaporate. And the largest contribution actually comes after evaporation. Let me explain to you how you compute this part here. So coming back to the source, to the equations of motion of these induced gravitational waves, now let me write it in terms of the velocities of the fluid, which is just the derivative of the curvature perturbation. What happened before is that in this primordial black hole dominated universe, these are, if you forget about primordial black hole, just think about dark matter with fluctuations. These are pressureless fluid, so they just collapse. There is no wave propagating or anything. Everything just collapses. So density fluctuations grow during this period. And then suddenly all the matter is transformed into radiation. So it's like a big explosion. And all these large fluctuations suddenly start to propagate. So you will have huge wake of waves. So you have huge velocities suddenly. So you will start from having zero velocities to propagating astronomical radiation with a huge amplitude. Okay? And this is the reason why you have an enhancement. So you have very loud signal because of this sudden evaporation. If you want to know the details, you can check these Inomatas papers, which I think they explain quite well. So in the end, you get something like this. So this is the estimate of the spectral density of these gravitational waves after evaporation. And it's a huge signal suppressed by the initial fraction and depends on the mass. So to compensate by this huge factor, you need this very small initial fraction of PBH. The spectrum looks like this figure on the right. Here you have the spectral density versus frequency. And I chose two masses. So the blue line is 10 to the 6 grams. The green line is 5 to the 8 grams. So this is just marginally okay with BBN. And the spectrum is like this. So it's very peaked. You have a single peak in one frequency. This frequency corresponds to the mean distance of the PBH. Beyond this frequency, I cannot say anything because we are working in a coarse-grained picture. So we treat these black holes as a fluid. So if you go to scale smaller than the main distance of the PBH, then this approximation is not okay. So here you have a cutoff. That's why they peak at this frequency. And you can use this estimate to constrain the initial fraction of PBH. So if you do that, then you get this blue line. The blue line is by requiring that, say, the peak of this induced gravitational wave is not in conflict with BBN bounds, okay, which I show in the black line. Then you get this blue bound. The red bound on the initial fraction is the minimum fraction you need so that the primordial black holes dominate the universe. Okay. Below this line, I mean, there is no real constraint, but primordial black holes do not dominate the universe. So if you want to test the primordial black hole dominated universe, it could only happen within these 2-3 orders of magnitude for a monochromatic mass. Now there's something interesting. So if the primordial black holes have spin, they actually can give some signal in the N effective, not detectable with current experiments, but maybe future CMB experiments can test it. Now there are some problems. So I think this case is interesting. So you can test the primordial black hole dominated universe, but there are some problems. And the worst one is that the primordial black hole density fluctuations, they grow. Okay, so the curvature fluctuation is always much more than 1. So we never leave the linear regime for the curvature perturbation. But if you look at the density fluctuations of this PBH, they eventually reach the nonlinear regime. Okay, so you have huge density fluctuations. This means that, well, black holes are actually merging, so that they are now closer. But depending on the mass, they can reach some huge values. So now the question is, can you fully trust this calculation where density fluctuations are nonlinear? Let me tell you that I think it's a good order of magnitude estimate, because the curvature perturbation is always much more than 1, and this is what sources induced gravitational waves. And I don't think that the production of gravitational wave will stop even if you reach the nonlinear regime. In any case, maybe you have more gravitational wave from the mergers and so on. If you want to study what happens in the nonlinear regime, then we will need some numerics. I'm not sure how to do that. Let's see. So I was a bit faster than expected. Do you have questions on this?
Actually, I have one question.
Yeah.
The primordial black holes which you are considering, which dominate the early universe, sometimes you spoke about dark matter. Are they supposed to model dark matter or?
No, sorry. This was just an analogy. So this is just, if you are familiar with dark matter, how they behave. So the initial stages, so all this evolution is the same as cold dark matter. But obviously, cold dark matter dominates the universe much later, and it cannot give anything like that, right? Yeah. But so if you forget about the time scales, the evolution of the perturbations is exactly the same. This energy density of pH and the fluctuations will evolve exactly as if they were cold dark matter. So this was actually the reason for this is because, so maybe I can go that. Let me show you. So the reason I was using this cold dark matter analogy is because you can actually generate gravitational waves from cold dark matter. And, oh, don't tell me that I forgot. Yes, here. Okay, so since we know that the isocurvature can generate gravitational waves now, you could also consider what happens if you have cold dark matter isocurvature. Huh? So we know that when dark matter dominates, it's too late and there will be no generation of gravitational waves, or relevant generation of gravitational waves. But can you compensate these suppressed gravitational waves with a large amplitude? And this is what we looked at this paper. Where is it? It doesn't appear. Okay, with Samuel and Sebastian Renaud-Petel, we looked into this. And so this is exactly what I was telling you about on these primordial black holes and the isocurvature. So this is the transfer functions for the curvature fluctuation, right? The isocurvature S and some relative velocity. You don't have to care about this with time. So what you can see is that in the beginning, there is no curvature fluctuations, and then they start to grow. And once they enter the horizon, they decay. Okay. So most of these suppressed induced gravitational waves will happen when this mode enters the horizon during radiation combination. And what Sasaki-san and Samuel showed is that so the isocurvature keeps growing and eventually reaches the nonlinear regime. maybe you form PVH, but it's not so important for the calculation of induced gravitational waves. They are generated much earlier when they cross the horizon. And now you can compute what is the induced. It's suppressed by the relative energy density at horizon crossing, but if you have large enough color matter isocurvature, you have a detectable signal. And for example, one estimate is that it will be proportional to the amplitude of isocurvature fluctuations suppressed by the ratio. This is the wave number at equality. This is, is it 0.01 megaparsec inverse? And then this is the scale of the, if you have a peak in the isocurvature. So this usually is huge. And the spectrum of the gravitational wave is similar. So this is the spectral density versus wave number or frequency. So you have here the adiabatic one in red and the isocurvature in blue. So they look more or less the same. There is no, so this minimum does not reach the zero and so on. The peak is in the same position, but the growth is a bit different and the IR scaling is the same. So you can say, you can ask the question, what is the amplitude of isocurvature fluctuations that we could constrain in the future? Okay. So this is the amplitude of the peak in the isocurvature fluctuations and say the moving wave number in megaparsec inverse. So of course you can constrain using the CMB now, and the constraint is quite tight. So it has to be 10 to the minus 10, 11. So 1% of the adiabatic ones. You have a mu distortion constraints, and then you have the constraints by future gravitational wave detectors. And this orange line is from the formation of PVH. So you can see that you can generate this detectable gravitational wave signal, but it's a parameter range where the amplitude of isocurvature is huge. So 10 to the 34 here, 10 to the 16 here. Sounds a bit crazy, but you are not out of the, say, the cosmological perturbation theory. So you have to think that the real amplitude of these fluctuations is density fluctuations, which is this times the energy density ratio. So this is very small when they enter the horizon. So this is sort of compensated. So we could also test cold dark matter. If there are huge isocurvature fluctuations in cold dark matter, we could also test it like this.
I think there's a question online. Sorry.
Yeah, I didn't see it. Yes.
Yeah, Guillem, thank you very much. I wanted to ask, why were you only focusing on the primordial black holes which were evaporating? Because it's the ones which, carry on, the ones, for example, which formed the QCD phase transition, they were still here, they could be the dark matter, and they're also detectable gravitational through their induced gravitational waves because of, the pulsar taming array. So I wasn't sure why you didn't focus on that scenario as well.
Right, so let me see. I can talk about this one that you're interested about too, but so the reason why I focused on the, the reason that I focused on this is because it's one of the, I think it may be the only way you can test if the primordial universe was dominated by primordial black holes. So otherwise these black holes, they evaporated and you don't know exactly how to test this scenario, right?
Yes, if they provide the dark matter, they're not actually going to dominate the early universe in this way. Yes, that's correct. But they can still generate gravitational waves.
Sure. So, okay, let me go to this. So this is the second part, which I didn't know if I had time to explain or not. So here, yes. So let me explain this a bit. So the scenario that you have in mind is that you have some peak that generates primordial black holes at horizon crossing, but they eventually do not evaporate. They have masses of solar masses or asteroid mass. They are still around, right? And they come from these adiabatic fluctuations. So these primordial black holes, they are formed at horizon crossing, and maybe I should explain this. So this is a Hubble diagram. You have physical length and e-falls. Okay, so here you have inflation in the beginning, and then usually you go to radiation domination until dark matter dominates. And so usually primordial black holes are generated during radiation-dominated universe. But if you change the expansion history, you will change the time when they enter the horizon if you fix the energy scale and so on. So let me show you how the spectral density depends on that. Yep. So there are different things here. Let me see. So I will consider you have a sharp peak in the primordial spectrum, which will lead to this sort of monochromatic primordial black holes. And if you are in radiation domination, you will have this red line here. You have a resonant peak at 2 times CS, the peak of the primordial spectrum. This resonance is because, so if you look at the equations of motion, oh my God. Yes, here. So this induced gravitational waves, the source is square of phi. Phi oscillates with a frequency given by the propagation speed times the typical wave number, CSKP. So because it's a square, you will have some resonance when this is 2 CSKP. So this is why you have this resonance here. But so this resonance depends very much on what was the content of the universe when these primordial black holes form and these induced gravitational waves form. And you could tell this equation of state apart because first, the position of the peak will change depending on the value of the propagation speed CS. Okay. And also the way it diverges, or the way it grows, it also depends on the equation of state. One curious case is this one, when CS is equal 1. And then there will be no resonance. So here by momentum conservation, the resonance is forbidden. So if you have these primordial black holes that form in a radiation-dominated universe, but not really radiation, so it's a canonical scalar field, then you will have no resonance, and this is how it looks like. You can also tell the equation of state of the universe apart if you look at the infrared tails. So here I show what happens if you have some stiffer equation of state. So now instead of decaying as k squared for delta, Dirac delta, or k cube for say not too sharp peak, then you will have a slower decay in the induced gravitation wave in the infrared. And here I show in the right-hand side what happens if the equation of state is softer than radiation, maybe even negative. Yeah. So the spectrum changes completely, and now it peaks at the heating scale. So by looking at the shape of the spectrum, you can tell whether these primordial black holes were generated during radiation-dominated universe or something different. Yeah. So initially I had more things about this, but for some reason I removed it. So this is something I want to explore, and yes. So in the scenario that you had in mind, these primordial black holes that could be, say, 100% of dark matter. Now, you will have a large gravitational wave counterpart. And my point is that the spectrum will actually depend a lot on what was the equation of state when this PBH formed. So I think primordial black holes are not too sensitive to that. So they just care about the mass. But induced gravitational waves can't really tell you if they were generated maybe during some other equation of state, so stiff or matter domination or something like that.
That is interesting, because if they form at the QCD epoch, we know that's because the equation of state does change slightly. You know, the sound speed dips by about 30% at the QCD epoch, and by other amounts around about that time. So you're saying there would be a way of testing that change in the sound speed using your gravitational wave analysis.
This is something I want to check. There is one paper by some Japanese people that I think they solve things numerically.
Yes.
And so there are two things. So one is that if so I'm thinking about some peak in the primordial spectrum. So if you're thinking about some almost scale invariant, then I'm not sure what will happen. So for a peak, it will only be interesting if the peak just falls in the QCD phase transition.
No, in this scenario, you don't have a peak. You have a relatively flat power spectrum, but you get an enhancement of PBH formation because of the sound speed dipping.
Yeah. In that case, I'm not exactly sure what will happen. It's not so obvious. So they are not like free gravitational waves. So it's not typical suppression. So something,
Right.
yeah.
Oh, but do think about that because it's my favorite scenario. So
yes, I had it in mind for a while, but so it looks a bit complicated. Yeah, that's why I didn't tackle it. Yes, but I think it's interesting.
anyway, thank you very much.
Thank you.
There's another hand up from Alex online. Alex, do you want to ask a question?
Can I ask?
Yeah.
Can I ask a question? Actually, it's even not a question, it's some remark. For formation of black holes and then radiation of gravitational waves, it takes some time. So it's not the most early universe which could be explored with the help of gravitational waves, because even more primordial primary gravitational waves can come from the very beginning, from epoch of quantum fluctuations. And they also give some information, of course, in absolutely different range of wavelengths, but nevertheless, all the stuff related with polarization of CMB and so on could give information about even earlier universe than you discussed today.
Yes, okay, I understand your question. I think you may have some confusion. So I'm not talking about the gravitational waves from the merger of these black holes, which happens much later. I'm talking, so these gravitational waves are really generated after inflation. So it's when these fluctuations enter the horizon, it's when these induced gravitational waves are generated. So it's
exactly what I said. But gravitational waves could be in the universe from the very beginning.
Yeah, you have the component generated during inflation, right? But the question is which one
just from the very beginning.
Yeah, from the, say, during inflation, right? But the question is which one is larger? And
yes, but they obviously should be of different wavelengths.
It depends. It depends on your model, actually. So you have, so to have primordial gravitational waves generated here, you need to touch a bit the inflation. And if you are thinking about these, I don't know, U1, gauge fields, axions, and so on, right? So they generate a peak in the primordial spectrum of gravitational waves, but they also generate these secondary ones, and they fall more or less in the same frequency band. So yeah, so if they come from the same mechanism, they will have similar similar frequencies. If they are unrelated, then of course it doesn't have to be, but this depends on the model. So if you want to have large, or maybe you are thinking about changing the equation of state or something like that.
No, I'm speaking about megaparsecs in gravitational waves with wavelengths today, megaparsec.
So B mode or something like that?
Yes, something, not B mode is polarization produced by these gravitational waves. But these gravitational waves can come from the very beginning.
Before... Yeah, this would be this. So here I just assume standard inflation, right? So it's a scale invariant primordial, so primary gravitational.
You speak about gravitational waves which are quadratic with respect to amplitude of initial perturbations, right?
Right.
I'm speaking about gravitational waves which of first order on initial perturbations, which are not generated, but which presented in the universe from the very beginning.
But you again, you are saying these primary gravitational waves during inflation, no? From quantum fluctuations.
Yes.
Yeah.
Yes.
Yes. So all my point is that it will depend on your models. You need to have some model in mind on how you, so usually if you assume standard inflation, nothing strange happens, then you have to suppress amplitude, right? You will not see it. So you need to somehow, at least in the frequency of gravitational wave detectors, you need to somehow enhance it.
Okay, thank you.
Another question in the room.
Can you hear me?
Yeah.
So I really like the idea of the phase in which primordial black holes dominate, and in particular, I would like to ask you if you think that the results that you have represented in after that, like the gravitational waves that are induced in this scenario.
So say again, like your question, I think I didn't get it.
So I was asked, I wonder whether you think that the results for the gravitational waves that come from this scenario will change when you include all the other effects that you said that need to be taken into account.
Well, yeah, I think the spectral shape will change, yes. And the amplitude, I can tell you, the amplitude depends on the mass function of the primordial black holes. And the reason is that, so here they evaporate suddenly because it's only one mass and they evaporate at the same time, right? But if the mass function is broad, this transition will be also sort of gradual. Okay? And the amplification of these induced gravitational waves crucially relies on this huge wake of waves. So now when the mass function is gradual, it's not monochromatic, it has some width, then this will also have some width and you will suppress the amplitude.
Okay.
I think this is the most important effect. And then nonlinearities, I'm not exactly sure what will happen, but it shouldn't change too much the amplitude. Of course, you can put a cutoff if you want when you reach the nonlinear regime. I don't know.
Okay. Because I was, there are some inflationary models that produce only primordial black holes that are evaporated by today in order to be consistent with the large scale measurement of the spectrum, like from alpha attractors in particular, I have in mind. And so that would be an interesting way of testing those models, because on the other hand, you cannot test them on the scales where gravitational wave observatories operate at the moment, because the peak of that secondary gravitational wave is beyond LIGO scales.
Right, but depending on the mass of the black holes, they should have some signal here. For example, if it's 10 to the 6th, then maybe Einstein telescope could see it.
So the takeaway message maybe is that the mass sets the scale where you will have the peak of this gravitational wave, and the broadness of the mass distribution will decide the amplitude.
Right. Yeah.
Cheers.
So you could. I think you can use it to constrain the initial amplitude. So and this will constrain your inflationary model, your alpha attractor, and so on. But the calculation with the finite width of the mass function, it's a bit more complicated. I would like to do it, but there are several problems, especially this nonlinear regime. So first, I would like to have a clear picture of what is really happening.
Thank you.
Do you know if they get a very broad mass spectrum, or so what is the width of
the mass spectrum? I have looked into it when I did calculate this the primordial black holes produced within these models, and it's not monochromatic. It's not really realistic to think about monochromatic spectra, I guess.
Maybe, yes. But do you know what is the, say, is it a log normal, or is it, what does it look like?
I didn't try to fit it with a log normal. But we can discuss about it. I have some plots.
Okay. Yeah. You can send me the plots and see how.
Okay, can I just comment that within inflation, it's fairly generic to get a log normal mass function. But of course, in other scenarios, like the QCD epoch, you get a very interesting spectrum which has a series of bumps.
Right.
But I mean, in general, as we just said, it's very unrealistic to assume a monochromatic mass function. That's hardly ever happens. Although I appreciate it's simple, it's the best assumption for making these sorts of calculations, but it's not really very realistic.
I'm not sure if the log normal is realistic as well. By work from Gao Burns.
Yeah, it just applies in a certain subset of models. I mean, it certainly doesn't apply in all models, and of course, many people have inflationary models where you specifically have a peak in the power spectrum just to produce PBHs, and that doesn't always produce log normal either. It's just it's just the simplest assumption, really.
All right, we seem to be past the hour.
Okay.
So I guess
can I say just a couple of things?
Realize we never let you get your.
I don't know if you are interested, but I'm organizing a workshop with the people in Padua. We are quite full already, but maybe we will have some streaming of the plenary talks. So if you are interested, I could let you know about this if we put this streaming. And if anybody wants to join, then you are very welcome. And then I also have some positions open. So I will start a new group in Hanover, and I offer 2 positions, 1 PhD and 1 postdoc for September 2023. And you can find the announcement in the Inspire website. If anybody is interested in working on these scalar-induced gravitational waves, then please feel free to apply. All right. So thank you very much.
Thank you.
I understand you have to leave quite promptly, so there's no time for a student.
Yeah, yes. I mean, if it's just 5 minutes, maybe it's okay. But if anybody has some quick question.
Just there's one more question online if you have time.
Right.
David, do you want to ask? Can I read your question? What do you prefer? Okay, I think I'll read it then. So the question is about primordial magnetic field fluctuations.
Oh.
The relative strength of acoustic density fluctuations versus the magnetic fluctuations. There's a large value of work about magnetic fluctuations.
Are you thinking about some primordial magnetogenesis scenario or something like this? I don't see why they should be related unless you give me some model of inflation. Yeah, so a priori they are unrelated. And usually if you don't have anything weird during inflation, this electromagnetic fluctuation should be small. All right, yeah. So, but probably you have some magnetogenesis in mind or something like this. Otherwise, I don't understand.
David says he'll send references.
Yeah, okay.
All right. Shall we?
That sounds like anyone wants to ask a quick question.
All right. Well, thank you very much for joining us.
Yeah, thank you. Bye-bye.
Bye.
Thank you. Thanks.